Before you dislike this video, I don't watch Dream, but I also have nothing against him. This is an entirely independent channel and I don't wish to be involved in any drama. I made this video because the math used in Dream's video and his astrophysicist paper was at best questionable, and judging by the comments, I don't think enough people know this. This video simply tries to explain this whole saga from a purely mathematical perspective, and I will not offer any value judgment of anyone involved. To get everyone up to speed, for those who don't know Dream/Minecraft, Dream is a very popular YouTuber and streamer who does these manhunt and speedrunning challenges, the latter of which would be the main focus here. Speedrunning in this context means defeating the Ender Dragon as quickly as you can. The part that we need for this video is that a speedrunner will mine gold and craft these gold ingots. Then you can go up to these piglins and throw gold at them. This trading process is known as bartering. The goal is that you get the Ender Pearl. This happens with probability 20 over 423, which is around 5%, and when you get Ender Pearls, you will get 4 to 8 of them. The other thing that speedrunners need to do is to go to these blazes and kill them. Then they might or might not drop a blaze rod. This drop happens with probability 1/2. With these blaze rods, you can craft blaze powder, and combining with the Ender Pearl that you got from bartering, you can craft an Eye of Ender. Usually, you will need about 10 to 12 of them to get to where the dragon is. The steps afterwards aren't important for this video. Now remember that during a bartering, on average out of 423 barters, we should expect around 20 successful ones. However, across Dream's 6 consecutive streams, out of 262 barters, there are 42 successful ones, which means around 16% success rate, which is a lot better than 5%. The data for blaze rod drop was also analyzed. The drop rate should be about 50-50, but Dream's success rate is 211 out of 305, which is about 69%, which again is quite significantly higher than the 50% expected. Okay, what if Dream was just very lucky? To quantify how lucky Dream was, we need to calculate the p-value. In this context, p-value is the probability that Dream had these success rates if he didn't cheat. The moderators did a mathematical analysis and said that a naive estimate of the p-value is in the order of 10 to the minus 23, which is roughly 1 in 26 trillion. However, this naive p-value does not factor in a lot of bias present, so they correct for these biases and came up with a p-value in the order of 10 to the minus 13, which is roughly 1 in 7.5 trillion. This p-value is so low that causes the moderators to conclude that Dream cheated. However, Dream then hired an astrophysicist who wrote this critique. They calculated the p-value to be around 10 to the minus 8, which is 1 in 100 million. And this p-value, although quite a bit larger than the one that the moderators calculated, is still quite small. However, since the latter paper is a critique, we would have to take a look at the first paper and see the math that they used. Let's consider flipping a loaded coin and suppose the probability of getting a head is p, then automatically the probability of getting a tail would be 1 minus p. If we flip this coin 5 times, for example, what is the probability we get exactly 2 heads? One possible sequence is 2 heads at the start, then all tails later on. There is probability p for each head and 1 minus p for each tail, so the probability of obtaining this exact sequence would be to multiply these probabilities together. However, we are not talking about this exact sequence because if these 2 results of the coin flips are swapped, there are still 2 heads. The probabilities only swap, and since we are multiplying them all together anyway, the probability of this second sequence is still p squared times 1 minus p whole cubed. It isn't difficult to see that the probability of each of the other similar sequences would be the same because we again just swap probabilities, and we will always see 2 p's and 3 1 minus p's here as long as there are 2 heads and 3 tails in a sequence. So all we need to do is to list all the sequences with 2 heads and 3 tails, and each sequence will have probability p squared 1 minus p cubed. So the final probability that we get would be adding these up, and we get 10p squared times 1 minus p cubed. The number 10 here represents the number of sequences of 5 coin flips with 2 heads. To simplify and generalize this, we use this symbol and reread this as 5 choose 2. More generally, the number of sequences of n coin flips with k heads is denoted n choose k. That means, in general, the probability of getting k heads in the sequence of n flips is this. To reiterate, this part is the probability of getting any particular sequence with k heads, and this part is the number of all such sequences. Alright, with this formula in mind, we can finally calculate some probabilities. Pearl bartering is also like flipping a coin, except the probability of getting a head, i.e. ender pearls, is 20 out of 423. The p-value we calculate would be the probability that anyone gets at least 42 heads out of 262 coin flips. In other words, the probability of being at least as lucky as Dream. We just need to substitute our formula above. So the probability of getting exactly 42 heads is this, then add on to the probability of being slightly luckier and get exactly 43 heads, and so on, until we add on to the probability of being the luckiest person and all barters are successful. Adding all these probabilities, we get an extremely small number. The moderation team actually gave a slightly larger number, but that's only because they round this probability up a little bit to 3 significant figures. This rounding up actually gives Dream a slight advantage. Okay, what about the blaze rod drop rates? We do the same thing again and calculate the probability of getting at least 211 heads out of 305 coin flips. We again substitute the formula to get the probability of getting exactly 211 heads and add up to getting as much as 305 heads. After adding all these, the probability is still insanely small, so basically, Dream got incredibly lucky in both Pearl trades and Blaze Rod drop. What if these two probabilities are correlated, and having lucky Pearl trades will also mean having lucky Blaze drops or vice versa? Unfortunately, no, because according to Minecraft code, these two events are entirely independent, so they couldn't influence each other. To calculate the probability that these two events happen simultaneously, we simply multiply these two probabilities together and get an even smaller number. Again, the moderation team's number is slightly bigger because they are rounding everything up to give Dream more advantage. This is a 1 in 26 tillion chance. This is a naive estimate, and we are going to correct for biases that might be present. Again, let's consider a coin, and your job is simply to find evidence that this coin is loaded, favoring heads more than tails, even if it is a perfectly fair coin. More specifically, you want the p-value to be less than a certain threshold alpha you choose. Let's suppose it is 5% in this toy example. How do we calculate the p-value? In general, if we have n coin flips and obtain k heads, then the p-value is the probability that we get at least k heads. This is something that we have done before already. One very malicious thing that you can do is that after each coin flip, we calculate the associated p-value. If you are incredibly lucky to have a lot of heads initially, then the p-value can drop below the threshold alpha that you predetermined, and so you have achieved your goal. However, it is entirely possible that if you continue to flip more times, more tails would come up, and then the overall p-value actually rises above the threshold. In this example, the overall p-value is actually around 0.623, so the coin is fair after all. You basically stopped collecting data only because you have done your job. A graph might help understanding. Let's say the p-value threshold is alpha here. When you get more and more heads, the p-value drops below alpha, even though it is possible that the p-value might rise as you obtain more data. If we are not that malicious and collect all the data, then you will conclude that the coin is fair. But if it turns out the p-value drops below alpha even if we collect more data, then the p-value either just passed the threshold or sometime before. That means if we adopt our previous method of collecting data, then we will definitely conclude that the coin is unfair. In this situation, it is entirely possible that Dream actually just looked like he got very lucky, but if he continued streaming, the overall p-value might not be that small. So let's suppose the yellow portion refers to bartering on stream, i.e. at this point, Dream stopped streaming. If he continued to stream, the p-value might go up. Let's get this alpha down to exactly where the arrow points, or the final p-value that we calculated. This will give the best chance that the next p-value we calculate is higher than alpha. Now we want to know what is the probability that the p-value gets lower than alpha at any point during stream. Let's phrase it in another way. Let's consider a p-value below alpha to be evidence that Dream cheated. The question now basically means the probability that we get the evidence that Dream cheated on stream even if he didn't. This is our corrected p-value, which must be larger than alpha, the original p-value we started off with. Calculating the corrected p-value isn't easy or direct, but basically for the Pearl trade, the original p-value was around 5.58 times 10 to the minus 12, but after the correction described, this p-value roughly doubles. Again, the mod team gave a slightly larger figure because they round everything up at every opportunity. For Blaze Rods, the original p-value we calculated was roughly 8.79 times 10 to the minus 12, and after the correction, the p-value becomes 5 times the original. Before we move on, congratulations if you made it here. The first bias is the hardest to explain and correct for, and I promise you have gone through the most difficult part of the video. In reality, Dream did 11 streams for his speedrun attempts, and the moderation team only considered 6 of them. The reason why they did not check those 6 streams instead is actually that these 6 streams are the most suspicious, so we aren't really taking a truly random sample here. This is a source of bias. If we always consider consecutive streams, what is the probability that at least one sequence of streams gives such low p-value? Even though we want at least one, we first consider no sequence of streams being suspicious. The probability of one particular sequence of streams not having a low p-value is simply 1 minus p. And if no sequence is suspicious, the probability is this to the power m, the number of all sequences of consecutive streams. Now, if it is not no sequence is suspicious, then at least one sequence is suspicious, so we simply need to subtract this probability from 1. How many sequences of streams can there be? Well, there is one consecutive 11 streams, 2 sequences of consecutive 10 streams, and so on, until we have all the individual streams counted as consecutive 1 stream. So the total number of sequences of streams is 1 plus 2 plus all the way to 11, which is 66. So this expression will be the revised p-value after correcting for this bias. Since we are collecting both Pearl Trade and Blaze Rod data from the same streams, we only need to correct this bias once. The moderation team actually looked at this case because of the Pearl Trades, so we correct the p-value for Pearl Trade only. The p-value from the previous bias correction was 1.19 times 10 to the minus 12, and this boosts the probability up by an order of magnitude. For the Blaze Rod, we don't have to correct the p-value this way, so it stays like this. Why do we need to pick on Dream? There are many speedrunners online attempting a world record. Surely, one of them can get that lucky. The correction for this bias is the same as the last one. We ask, what is the probability that any speedrunner gets this lucky? Well, the same formula applies here because the previous bias just replaced the word speedrunner by consecutive streams. So M here does not represent the number of consecutive streams, but instead the total number of speedrunners. The moderation team estimated that the total number of speedrunners in the community is 1,000, so we substitute M to be 1,000. Again, we only need to correct for the portraits because we collected data from the same streams, certainly the same person, so applying this formula to the p-value that we previously obtained, we have boosted the probability by 3 orders of magnitude. The blaze rod p-value stays unchanged. Then we need a sensible way of combining these two figures into a single p-value. This is done using what's called the Fisher's method, a popular technique of combining p-values, and the combined p-value is an even smaller figure here, so we are done, right? Okay, I promise this is the last one the moderation team actually considered. Why do we only consider the pearls and blaze rods? There are so many pairs that can be analyzed. Surely, one pair will give you p-value that small, right? It looks like we can again use this formula that we have seen twice before, but when we take the power m, we implicitly assumed that these pairs are independent. But this is not the case here, because if you are particularly lucky in getting an ender pearl from a barter, then your chances of getting anything else in a barter would be lower. So we need to use another approach. For each pair, we find the probability we get the p-value to be lower than p. Well, by definition of p-values, the probabilities would have to be p. We now simply add these probabilities up, so the corrected p-value would simply be multiplying by n, the number of pairs we can analyze. This is actually an overestimate, because in the case that both pairs have p-value that low, we would have counted it twice. So let's use this overestimate, and we now need to calculate the total number of pairs. The moderation team estimates that they only analyze at most 10 Minecraft items, so there are 10 choices for the moderators in the first item that they analyzed, and 9 choices for the second item, because an item had been chosen and we don't repeat. So there are at most 90 sets of data that the moderators have collected. Now let's pull up the combined p-value that we obtained previously, and we simply have to multiply by 90. And finally, we get this final p-value. Again, the mod team gave a slightly larger figure and quoted from the report itself, this is the loose upper bound on the chance that anyone in the Minecraft speedrunning community would ever get luck comparable to Dreams. Phew, that was a lot of math involved. To summarize, we want to see how likely the pearl trade and blaze rod drop rates are, and we first do a naive estimate of the p-values, then we correct for the biases, first the stopping criterion for both p-values, then particularly for pearl trades we correct for stream and runner selection biases, and then we combine the two p-values using the Fisher method, and finally we consider the bias caused by potential p-hacking and got the final p-value. It looks like the mod team already gave Dream every bit of advantage possible, so what did Dream's astrophysicists criticize? The main argument the astrophysicists used was that in this flowchart, our naive estimate of the p-value was already wrong. Remember that our goal is to craft the Eye of Ender, so if we have enough Ender Pearls, we are good to go. So basically, when you look at the barter results, the last one is always successful because then the speedrunner moves on. This bumps up the success rate. If you continue trading, you might not get Ender Pearls at all, and the overall success rate is actually lower. However, does this sound familiar? The moderation team already accounted for this in the next step when they corrected for bias caused by early stopping. Plus, the effect caused by early stopping is not that significant because while in the first run we have earlier stopping, the next run will continue with more bartering. The effect will gradually diminish with more and more runs. Perhaps the astrophysicist wanted to say that even though we get 42 successful barters out of 262, since the last barter is successful anyway, we should only focus on the previous bartering results instead. The same goes for blaze rod drops. Then, the corrected naive estimate can then be fed into the same algorithm described previously, and we get again an insanely low p-value, which is larger than what the mod team calculated, but still, it is 1 in 1.6 trillion chance. This is only a factor of 5 increase at most. There are also minor criticisms from the astrophysicist about the incorrect stream and runner bias correction, as well as the p-hacking corrections. Instead of accounting for stream and runner bias separately, we consider the number of streams altogether. The paper estimated that there are 100,000 speedrun attempts per year, so the number of 6 consecutive lucky streams to investigate is also just roughly 100,000. So basically, the combined correction for streams and runner boosts the probability by 100,000 or 10 to the power 5. However, in the moderation team paper, the combined correction already gives this probability a 66,000 times boost. The p-hacking bias correction is also criticized because it is argued that the number of likely targets for investigation is 37, not 10, and so the number of choices for the second target is now 36, not 9 anymore. So now the number of pairs is not 90, but over 1,000. Basically, the correction for p-hacking boosts the probability by 1,332 times, and in the original paper by the moderation team, the probability boost is about 90 times. So even if I use the astrophysicist correction factors, I get 1.39 times 10 to the minus 11 as the p-value, which is still 1 in 72 billion. And I still have no idea how the astrophysicists came up with the 1 in 100 million chance figure here. However, what bugs me the most in this paper is this paragraph. It says, let's begin with the example discussed in the Minecraft speedrunning team report as an example, getting a run of 20 heads in the 100 coin tosses. So let's do that. Here are 100 coin flip results, and one sequence we will consider is to have all 20 heads right at the front. We don't actually have to care about anything thereafter because we are only interested in whether there is a run of 20 heads. The probability of this happening is 1 in 2 to the 20. However, it is also possible to have the run somewhere in the middle, and again, the probability of having the run in these 20 positions is 1 in 2 to the 20. There are altogether 81 places where consecutive runs are possible, from the first 20 positions to the last 20 positions, so we simply have to multiply this probability by 81. This is an overestimate because all sequences that have a run of 20 heads is counted, and for cases like the first 21 flips are heads, we have even double counted, so this 81 over 2 to the 20 works as an overestimate. The paper actually thinks our logic does not work, and says that reading over the MathWorld page and performing a simple Monte Carlo simulation shows that it is not that simple. The actual odds come out to be about 1 in 6,300. This is the formula from the MathWorld page referred, and P is the probability of getting ahead, which is a half in this case, and R is the number of runs we want, which is 20 in this case. So this formula here is simply a function of the parameter S, which can then be expressed in terms of a series. Then the probability that we want is simply adding all these coefficients up until a point determined by how many coin flips we are considering. If we use a computer, this is the exact probability that there is a run of 20 heads, no approximations whatsoever. This turns out to be about 3.91 times 10 to the minus 5, or 1 in 25,575, which is certainly far lower than 1 in 6,300. If an exact analytic solution isn't your cup of tea, let's use a Monte Carlo simulation like what the author probably did. Because it is supposed to be simple, the author hasn't actually provided the code, but this is what I assume he did. First, we run a series of 100 coin flips, then check whether there is a run of 20 heads. Repeat this for a lot of times, then calculate the proportion of those with runs of 20 heads. I did 10 million trials, or basically a billion coin flips, and 397 of those trials have a run of 20 heads. This means our estimated probability is 3.97 times 10 to the minus 5, which is about 1 in 25,189. Again, this is way smaller than 1 in 6,300, and I have no idea where this number comes from. There is actually a third method in solving this problem using Markov chains. If you are interested, I have put a link in the description. And don't get me started on the code snippet here. The author tried to simulate the pearl trade giving 4 to 8 ender pearls like what they did in Minecraft, but if you actually run the code, you can never get 8 ender pearls because the NumPy random function here is always non-negative but smaller than 1. Even if it can reach 1, this NumPy round function will actually round 4.5 down to 4, so the maximum we get is 7 ender pearls. Now I want to emphasize that this video is meant to be a purely mathematical analysis and I don't want to offer any value judgment. All I'm trying to do is to criticize the math used by astrophysicists, not the character of Dream or the astrophysicist. I actually started making this video as soon as Dream posted this response, but videos like this on my channel took a long time to produce. So if you do make it here, really do consider liking this video, subscribe and hit the bell notification, as well as commenting on it so that more people can watch this. See you next time.